So now this is lecture 52 and we are continuing with our discussion about degree. Okay. So recall that degree of V of I is a homogeneous polynomial ring, ideal in a polynomial ring n plus 1 variables. So this is homogeneous, ideal. Okay. So degree of V of I, we defined this to be the multiplicity of S mod of S mod I, okay. And just a remark, this is not really a new result. If dimension of V of I is D, okay, or equivalently the dimension of S mod I is D plus 1, okay, then the Hilbert polynomial of S mod I is of the form EI Pi. I goes from 0 to D. D is 1 less than the dimension of the ring, and with ED is not 0. ED is actually positive. Okay. These are integers, okay. And so then ED is the degree of V of I. Okay. Just a remark that you should be familiar with. Okay. Let's look at a couple of examples. So here is an example of computing degree. So we take a polynomial ring in some large characteristic. For these polynomials, even if you take even if this is a finite field, but one would still have enough linear forms. Okay, at least the way we have set this up. So we take the ideal to be this this y square minus xz, okay, and x is proj of. So in Macaulay there is a command called proj for a graded quotient ring. So we can just say x is proj of R mod I. Okay. So let's look at this. So this is a three-dimensional polynomial ring, and in which we are going modulo 1 equation. Okay. So this just happens to be prime, okay, but we're going modulo 1 equation, and then we know that the dimension drops exactly by 1. This was a consequence of the dimension theorem, Krull principal ideal theorem, etc. Okay, so dimension drops exactly by 1. Therefore, R mod I has dimension 2. Okay, so we ask questions to Macaulay. Okay, so we ask for its degree. Okay, so if we ask x is equal to proj R mod I, it would say x projective variety. So it is of type projective variety, and you can ask for help or methods to figure out what all things can you do with a projective variety. Okay. So one command is degree of x. So we ask for degree of x, it gives out 2, and dimension of x, it gives out 1. So let's we'll worry about the degree afterwards, but let's just look at dimension. R mod I is, as I mentioned, 2-dimensional. Ambient polynomial ring is 3-dimensional, going modulo 1 equation. So we have 2-dimensional, and then we have this. Okay. So let's ask. So we can ask this question to Macaulay: how is it computing dimension of a projective variety? So there's this command called code. So code, and then we give the as an input, as a sequence, we just give all of them. So dim is a command, and this is the type of the input to the command. So code. So this is asking what is the code to compute dim of a projective variety. Okay. So it says dim of a projective variety. So this is a function. This is defining a function. So it is a function, okay, which takes x to the dimension of the ring of x to -1. So this is how we have been discussing dimension of a projective variety. Okay, so this is not surprising at all, and it's a good idea to sort of try to understand how something is computed, at least so that maybe we don't understand, but at least as much as we can understand, we can see that the computations are correct. Macaulay has been around for some time, and all of this code is public, so it is. If there are mistakes in these, people would have noticed it. But okay. So let's ask. Okay. So now you should do this yourself. How is the dim of a quotient ring computed? So you give code in brackets dim comma quotient ring. It will tell you how that is computed, and then sort of you do it multiple times repeatedly to figure out how it's going. So as an exercise, do this. Okay. But let's ask what these quantities are. Let's ask for ring of x. Ring of x is this. Then ask for its dimension. Ring of x, and then dim OO is just the dimension of the previous output. Okay. So what is the? When we ask for dim of x, it tells us it is R mod y square minus xz. I mean, we knew this, but it's a good idea to run these commands and check. And it is of type quotient ring. Okay. And we ask for its dimension, it is 2. Okay. So it is, this dimension of the projective variety is computed exactly as we were discussing in the lecture. Okay. So the ring is 2-dimensional, and Vi is inside P2, 3 variables. So it's P2 is 1-dimensional. Okay. Now let's see what this intersection with open sets looks like. Okay. So this is a little trick. Okay. What we really need is we should map the polynomial ring, okay, to a new ring in which x goes. There was x, y, and z. The y and z should be, I'm sorry, there was a typo here. This should be z1. Okay, so it should be mapped to a polynomial ring in three variables. X as it is itself. Y1 as y1 should be what is y over x, and y2 should be what is y over sorry, not y2, z1. Z1 over z1 should be z over x. Okay, so that's what is written here. X times z1 is z. So with this ring map, if you extend I, okay, and then invert x, then we would just get a polynomial which involves constants y1 and y2, okay, because it is homogeneous. Okay, so just think about this. If you have a homogeneous polynomial and we make this substitution, homogeneous polynomial x, y, z, and y we substitute as x times y1, and z we substitute as x times z1, then that whole polynomial will now be x to the degree, the common degree, the homogeneous degree, times some polynomial which does not involve x at all, which involves just constants y1 and z1. Okay. So that's what you have to do, but the cheap trick is just to substitute x to be x to 1. Okay. So this is just a trick. Okay. It just works. Okay, so Ix we just substitute as x equals 1. So remember, this is the equation. Okay, so if you do this correct operation, we would just get y1 square minus z1, but just call y1 and z1 as y and z. We just got this. Okay. So on that open set, okay, which is like spec of k y z, this x is defined by y square minus z. So in real picture, it's a parabola. Okay, so what we have done here is just a shortcut. Okay, the y and z that we see here are really this y1 and z1. So keep that in mind. So x intersect ux looks like a parabola. Assuming that we are plotting the real values. Okay, but it's only to keep a picture in mind. And we can similarly do iy, in which we divide the polynomial by y and then remove that part, and so then it would be xz plus 1, xz minus 1, okay, or 1 minus xz. So it's just like setting y to 1. Okay. Again, remember that this x and z are not the x and z of R. This is really the ratios of x and z to y, x over y, z over y. Okay. So that's a different. So it's like a over R. It looks like an hyperbola, and in this the case of z should be same as same as x, because there's not. I mean, x and z are interchangeable the way it is described. Okay. So x, this looks like ux. So now what we would like is to go modulo. This is a one-dimensional set. We saw that topological. We saw that if we can go modulo one equation and then check what happens. Okay. So I took a random polynomial, and as we talked about it earlier, if the field is large enough, then theorems for which we are look for general elements will probably work if you run the random command. Again, this is just a belief. There is no proof, but if you run the random command enough times, the result that we would get would agree with what the general linear form argument would give. Okay, so now we can ask dimension of the variety of ideal of L. We could have just asked projective variety also. Okay, if a homogeneous ideal, variety command will produce a projective variety, and it says it is 1. Again, in P2, we go modulo 1 equation. So the 3 variables became now 2 variables, and after some change of variables, it became 2 variables, and its proj is one-dimensional. So that's what we have here. Okay, and let's look at why is it called a linear form? Well, it's okay. Well, look, if you do this here, inside P2, it looks like a line. This is some linear equation whose solution would be y. Okay, so this is a line in Ux, and similarly, by looking at this, if you invert y, if you invert z, any of them, it will all look like lines. Okay. Now let's ask, if you take minimal primes, so this is slightly longish command, ideal of the ring of X, which was y square minus xz, plus ideal of L, which is the general form that we just constructed here on top. Here, this one. Okay. So, then let's take a Grobner basis, because if you just write the sum of these two ideals, you'll just put the generators together. It won't tell us, it won't sort of simplify it for us. So we ask for a Grobner basis. Then we ask for its generators, and so we want to convert we don't want Grobner basis. The output of GB command is of type Grobner basis. We want an actual ideal. We don't want the extra structures associated. For that, we just do ideal gens GB. Okay, so much of it tells us what this ideal is: y square plus y square minus zx, comma general linear form. Okay, that ideal is, and then we ask for its minimal primes, which, as I said, we have not discussed how that is computed, but at least we know that there is a command which will compute it, and it shows us 2 ideals. Okay, if we notice, both of these are homogeneous linear forms. So let's look at this ideal. Inside P2, this will cut down dimension by 1. This is linearly independent from that, so we'll cut the dimension once more by 1, and so this is actually a point with multiplicity 1. There is no extra multiplicity here. Similarly, the same argument, these 2 forms are linearly independent, so they'll cut dimension by 2. So we started with P2. I mean, every chain of homogeneous primes had length 2 in it, excluding the maximal ideal, had length 2 in it, and we cut 2 of them. Now it has length 0. So this is also a point, and its multiplicity is 1, because if you write out this ideal and compute its Hilbert polynomial, we would just get P0. Okay, so this is the thing, and so VL VL intersect X. This is what we had mentioned in the theorem. Consists of 2 distinct points. Okay, so this is the theorem in the previous lecture. So now we look at Hilbert polynomial of X. So it is minus P0 plus 2 times P1, and as we notice, that its dimension is 1, this P1's 1 says its dimension is that, and coefficient of P1 is 2, which was the degree. So if you just compute the Hilbert polynomial of a projective variety in Macaulay, it would tell us what the degree and dimension is. Just this exponent here is the degree, is the dimension, and this coefficient, this coefficient 2 here is the degree. Okay, so this is just preliminary things about computing degree. Okay, so the next example we will discuss a little later after we worry. So now we want to worry about why care about these homogeneous proj and homogeneous ideals, etc. Why not just work with spec and Kn? So this is question. Why worry about proj? It already looks very complicated construction. Proj of n, a ring in n plus 1 variables, and instead of spec, okay, or Kn. I mean, equivalently, if you are working over an algebraically closed field, just Kn. Why not? I mean, why do this? Okay. What is the advantage of doing graded things over non-graded things? Okay. So this is a little. I mean, there's no direct justification for this. Okay. So we'll see a few things here and there in the next 2 to 3 lectures. Okay. So the motivation is that Pn, well, this is a very loose statement, is compact. Of course, we have not, that's not in a affine space. If you look at the risky topology, that is also compact. It would satisfy the definition of compact. That's not what we mean this thing. So I put it in quotes. And so this projective space or the proj of a ring has a polynomial over a field has certain more desirable topological properties than An. As we said, we have not discussed a lot of the scheme theoretic issue. I mean, any of the scheme theoretic issues behind this. We haven't even defined what a scheme is. So I will not attempt to justify this. But let's. It is possible. I mean, it's likely that you have seen an example of this in complex analysis, in undergraduate complex analysis. So if you've not seen it, it is okay. Just ignore this, and okay. So consider C and consider the Riemann sphere. So which I will just denote by this. This is C union some. It's a one-point compactification Riemann sphere. Okay. Suppose we take a polynomial in one variable. Okay. Then if we look at C, well, it has no poles. It's it's an entire function. It's a holomorphic all over on C, and let's say degree is n, and for simplicity, let's assume it's not constant. Okay, so positive degree. I mean, it is true for constants also, but okay. If we think of C as a function from f as a function from C to C, it has n zeros. That's a fundamental theorem of algebra. Okay. F gives a function from C to C that has n zeros. Okay. Fundamental theorem of algebra. I mean, some version of it, saying polynomial splits into linear forms. Okay, so this is I mean, okay, but if you think of f as a function from the Riemann sphere to itself, then it has the same number of zeros and the same number of poles. because poles, well, infinity is a pole of order degree of n. So it's like same number of poles counted with multiplicity, poles and zeros, okay, counted with multiplicity. Again, when we say it has n zeros, this is counted with multiplicity. I mean, it is possible that f is just some x minus 1 squared, okay, counted with multiplicity. Okay. I mean, if you have a polynomial of degree n around the point infinity inside here, okay, it would look like, I mean, if you change coordinates, it would look like z to the minus n. So therefore, its number of poles is equal to the degree. That's the thing. So the point is order of the pole at infinity inside this point is degree of f. So there is some, so bringing in this point C, point to make C the Riemann sphere has this advantage that in functions, for polynomial functions, it brings in a symmetry between poles and zeros. Now if you look at rational functions, then this is, I mean, therefore this is true for all rational functions also. If you have a rational function f over g, f divided by g, well the poles and for both f and for g, because they are polynomials, the statement is true. So therefore it's true for f divided by g also. Okay. And we do, okay, so, and what is a pole for f would be a pole 0 for 1 over f and so on. Okay, if you look at it, if you work in this context. So it brings in some extra structure or some symmetry that can possibly be used. Okay. So this is so let's say one motivation. Okay. It's not without actually proving without actually making sense of what this quote unquote compact is and proving the statement, I won't be able to make sense of it any further, and I will not try to attempt that in this course. Okay, so another point, so this is one thing. Another example. Why going for this this bigger space is desirable? In fact, again, we won't prove it. We can think of C as spec of Cx, and then C hat as proj of Cxy. This is okay. So therefore, the passage from C to C hat is exactly like the passage from proj of a polynomial ring in one variable to proj of, spec of a polynomial ring in one variable to proj of a polynomial ring in two variables. Remember, we have to, if there are n plus 1 variables in the corresponding affine piece, there are only n variables. Okay. Corresponding piece where you look at the spec, there are only n variables. Okay. So another example is if you take two lines in K2, okay, need not meet, or meets in one point. Okay. So this is, but if you take two lines in P2, okay, so this is, okay, but two lines in P2, which we said is proj of K x, y, z, always meet in exactly one point. Okay. And why is that? If you take, so let's say L1, L2, okay, not multiples of each other, so linear, not multiples of each other. L1 and L2 inside S1, linear forms each other. Okay. Then height of the ideal generated by L1, L2 is 2. So therefore, dimension, we don't need that, we don't need therefore here. Dimension of S mod L1, L2 is 1. So it gives a point. And more importantly, degree of S mod L1, L2, L1 comma L2. So if you go modulo 1 element, this is the same as degree of S. That's because we saw that, not degree, we should say multiplicity of this is equal to multiplicity of S. This going modulo 1 element, one non-zero divisor does not change multiplicity. I mean, we used it in the other direction to prove something about the numerator of the Hilbert series, but this, the equality is what we want. And this is the multiplicity of S mod L1, L2. Okay. So they do intersect, and they do intersect with one point with no multiplicity, one simple point. Okay. So in project, so so 2 points in projective space, all 2 lines in projective space, in projective 2 space always intersect, while 2 lines in K2 need not intersect. Okay. So there are these nice properties that one has when one works with examples, right? In the graded situation. Okay. So let's look at this Macaulay code. So this is just restating whatever we did, just to get. So 2 lines in K2 intersect. So 2 random lines in K2 will intersect. So what have we done? So here, so this is a long way of just generating 2 random elements. So what have we done? So forget about Gen's GB ideal. What we are concerned about is what does this thing between this leftmost bracket and rightmost bracket do? So here is a sequence 1, 2. Now apply to every element in this. So this sequence slash a function is just a shorthand for the apply function. So apply to every function, apply to every element of this, the function, which takes I to the sum of some things. Okay. Now what are those things? Take the list 0, 1, and to this list apply the function d. So d is either 0 or 1. D is first 0 and then 1. A random element of degree d in R. So what it is saying is, for each I, pick first a random element of degree 0 and then a random element of degree 1, take the sum. So this is just an inhomogeneous polynomial of degree at most 1. So that's what this sum open bracket corresponding close bracket gives. And do this for I equals 1 and I equals 2, meaning to generate two inhomogeneous linear polynomials. Linear polynomials with a constant term. Okay, so we want. Okay, so and then we ask it to simplify the expression. So Gen's GB ideal. So then it says so this thing. That ideal has a solution. Y equals. Y plus 4078 is 0 and x minus this number is 0. So in other words, 13604 comma 4078 is a solution to this equation. So these two lines, the lines that were randomly generated, they do meet. Okay, so just an example. And parallel lines, it's very easy, just like x plus y and x plus y plus 1. And clearly, if you ask for this thing, one is in the ideal. So this is not going to meet anyway. Okay. So that's what we mean. Okay, so this has to do with the next topics, which we will do in the next lecture.